So let's gonna change topic and deal with some performance tips. We already discussed some of these across these lessons, but let's gonna reunite and put them all in one place here. So here I'm giving some suggestion for issues that matter for performances. And the first one is type stability. Again, type stability of a function is a property that guarantees to the compiler that when the function is called with some certain type of the argument, the output returned is of a given type. It doesn't need to be the same, but given some type of argument, the returned type is fixed, and this allows to continue the type inference across different function calls. So function A that call function B that call function C, and so on. And here I make you two examples of functions, the same functions, but the first one is type unstable and the second one is type stable. So the type unstable functions, I have a vector here. Using this syntax here, this out vector is of type any. The compiler cannot recognize what is it about. It just creates a vector of any elements, and then exactly which element depend on the x of the value of the x. The second one instead, it convert this out vector all to integers, so that as the elements here are all integers, also this out vector is an out vector of integer. So when I call it, whatever is 1, 2 or 3, the results will always be an integer. And by the way, now I also notice that here I don't need to do this one. Whatever I put out of a out vector here is a type any, so this is type stable even if I don't put this if loop. But let's gonna do it so that the two are the same. So I have these two functions, so I call it A and B, and you can see here that this is a float and this is a string, and for C, I call C and D with the same parameter, but I always have an integer. And I can benchmark these two functions using the package, where is it? Benchmark tools. And use the macro btime. So btime, it's allow us to avoid measuring compiling time. And when I call the first function, I have 626 against 54 nanoseconds. So you can see here, but even if this f2 seems to do more work, because here it has to make a convert, here has to make a parse. Even if this has to make more work than this one where it just return the output of a vector, it take much more memory and more than 10 times more time. We have a macro here, code warn type, that tell us exactly this one, if function is type stable or not, and we get this one from this body here. So here is red any. This tells us that f1 is not type stable, and if I do the same with f2, we have a reassuring body int64 that tells us that the result of this call with this type integer, it will always be an integer. Still related to type stability, one note on annotation. You almost never want to annotate a function for performance. It will not change nothing from a performance point of view to annotate an argument of a function, but it is important to annotate the fields of structure and do that with concrete type and not with abstract types. And I show you why here. So here I create an abstract type and two subtypes of this abstract type, foo and boo, where one has a field x of number, where number is an abstract type, and here boo has a field x annotated to be an integer, so a concrete type. And then I have a function f1 that take go and take x value and add plus. So I can call this function f1. Sorry, first I create the two objects, and then I can call this function f1 with either foo or boo, because both are a subtype of go, so they will go here. They will create, these two calls will create two methods, one specific for foo and one specific for boo. And we'll see here that the time is very different again, 17 times. Actually, it doesn't create methods, sorry, I was wrong. It doesn't create new methods here. But it calls the same method with two different subtypes. And you can see that because this type here is boo is made of all concrete types, the time that f1 take is much lower, and we can see here that this one is type unstable, and when I call it with b_obj with this specific type, I have an integer as results, and it is type stable. Another important and relatively easy to implement solution to improve efficiency is to avoid global variables, and in particular non-constant global variables. But what is a constant global variables? Well, let's gonna put here a global variable and a constant global variable that is defined with the const keyword. Attention that constant doesn't mean it cannot change value. We can rebind our constant to another object, but it must be of the same type, and we get a warning, but we don't get an error. We still can do it. What we cannot do is we cannot rebind this constant variable to another type. This is what constant actually means. So we are guaranteed that the variable is binded to an object of a given type. Then what is the object? Actual object could change. And I'm going to take three functions. f1 take two variables, both given as a parameter. The f2 sum with our global, and f3 sum with our constant global. And I'm going to benchmark, and we can see here, wow, the difference, just because this one, so this where all the information that is needed by f1 is given as parameter, or this f3 where the global information is declared constants, they are hundreds of times more performant than f2. So sometimes you may have a very bad performance by simply because you are using some global constants, and then in that case it's simple, or you add constant, or you put this constant in this variable as a parameter of the function. Another element for improving performances is to consider that Julia is column major, and this is different from Python that is row major. What does it mean? That when you create a matrix or an array for any dimensions, it is across the first dimension, across the different row of one column where the data is actually stored. So if we have a matrix like this, the data in memory follow the first column, and then it go in memory to the second column, and then it go to the third column, and so on. And then the idea that is a matrix is just reshaping of the data, but the data in the memory is just a line one after another one of the different row of the same column. So let's gonna create a relatively large matrix, and let's gonna to create two functions. The first one loop for each row and then loop for each column, and the second one will loop for each column and then for each row. Which one do you think will be faster? Okay, which one will be faster? You can pause if you want. So what these are doing? This one is going for each row. So I'm row here, and then go column 1, column 2, column 3, column 4, then row 2, column 1, column 2, column 3, column 2, row 3, column 1, column 2, column 3, and so on. You can see here that the loop is not continuous to the memory. It goes here, then it goes to somewhere very different in memory, 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 and so on. While F2, it go for each column and then for each row. So you go here, 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 and then go back to the first row, second column, second row, third row, fourth. You can see here that is all continuous in memory, then continuous in memory, and so on. So it is evident at this time that when I benchmark, the second one will be faster. Actually, it's not much difference, but because the matrix is not very big, if with a bigger matrix, you would see the difference more. So these are all elements important for improving performances. Okay, you can improve performances, but in the first instance, how can you find where your code need improvement of the performances? This is called profiling, but is it going to your code and analyzing which are the parts of your code that take more time or more resources in general. So we already see that you can benchmark a single function with btime or a benchmark macro. So I don't go into here because we already saw this one. You have another useful macro that is called profile. What is this one? This uses a sample-based profiling, because sometimes profiling can slow down your applications, but sample-based profiling are very efficient because it's like a tick that is coming every few milliseconds, and when the tick happens, it measures in which line your code is. So it measures in which function is the tick, when the tick happens, in which function your code is. So you need to use this profile from the standard library. And here we have functions that do three things. We don't know which one are more time consuming. Here is initializing a random matrix. Here is summing up, and here is multiplying and returning the result of the multiplication of the two summation of this random number. So as this is very small and very fast, we can put our profile under a macro when we run 1000 times this function here, and we see where and we profile the function. And after this is done, I don't know, yeah, it was quick, we can print the profiling. Let's see if it does it here or here, because if it does it here, I'm going, yeah, okay, it does it here. What is this? Oh, let's gonna see. So here, so this profile is giving me the time, the no, it's not the time, but is the number of times that the tick happened in this specific function. So here is 1450 continue here, so this is not spending time. Here we started seeing macro expansion foo. Okay, so here is the macro expansion, here is starting the code. So here we have already see that we're spending 400 of this tick here in this random to call this rand function. So this is the further top is 574. So this line 574 is this one, and is taking 400 ticks, and then this is called the random function. So this is the inner function. We don't want to know where is exactly, we don't care where inside the random, but it's the random function that is taking 400 ticks. And then the next one is here, 575 is taking 134. So we take that this addition, it takes 1/4 of the time of this random. And then, okay, here go broadcast blah blah blah. We don't want to know this one, but this is the other one. Further top is 576, that is here the multiplication 916, and all is the call to matmul, that is the inner multiplication of matrix used, but at the end it used the BLAS library. So you can see here that the relative time, we don't know how many seconds, but in relative times we already know that this multiplication take roughly double than this random number generator, and that in turn it's 4 times more time consuming than this plus operation. So this is very useful when you want to know where your code is spending time. And after you are done, you can, before you run another one, as every time you run, it add ticks. It doesn't clear. To clear the profile, you use the clear function, and then you can use it for something else. So aside this benchmarking b time or benchmark macro and this profile time macro, we have other functions to introspect and debug our code, to find problem more in general to our code. So you want to see the source code of some method. Well, we have something here less, and it gives us, yeah, this is the source code of the program. Here's exactly here, but maybe some foo is a function that you, for example, you want to know rand, where is rand is coming from. You want to see the source code of rand. And here is the source code where is defined the round function, and you want to edit it. Well, why not? We have edit. So if you have then I think it's opening now an external editor. Okay, yeah, it just takes a little bit more time. but here I can edit. If I have writing access to this file that is part of the Julia standard library, I can edit my function. So this is very useful. These two are very useful macros. Okay, then you want to know all the methods of a functions. You have methods and telling us there are two methods. The one that we defined, one without argument and one with one argument. Of this one, which method will be called with this particular argument, and tell us where is it with the command line at 573, so he will use this definition, this method here. What else? We already saw type of and L type, that give us the type of an element contained inside another one, which are the field names of a type X. We can dump an object and again know everything about it. We can, for a modus, and main is the main modus, we can retrieve all the names defined in that modus, and I can give all to get all the, including the non-exported one, or if if I say all false, I get only those exported, all that are available. If I put all equal true, I will get also those that are not exported by the module. And here I have all the names, variables and functions in the main module where I am working. Here I give the size of one in bytes of one object. Why this is 8? Because integer is 64-bit. 64-bit is 8 bytes. And if I want to know which is the maximum number that I can get from an object of a given type, I can get type min and type max, and I think we already say bit strings that give a string representation of the bits of an object. And we have then various low-level interpretation of an expression, where code native, code LLM, code typed, and code lower, they're all different, really what's happening at the very low level of your Julia code. So you can really see that here you can go really inside and inspect what is really happening at the very low level of the memory, and is really useful if you know what you are doing. Okay, and to finish here, we can use a debugger. I'm not going to show here, but here you have a debugger here, the same in Juno, and the typical way here, you can see here, you can put breakpoints and then run some code, and the code will stop at your breakpoint. So if you put your breakpoint within a function, the execution of your code will stop here, and you can inspect the local variables local to your function, and from here then you can go one line, or you can go inside. For example, if I put my breakpoint here, I can then go inside and inspect the random function, or I can just execute the random function and go to next line, or I can go out of the function altogether. Still another topic, runtime exceptions. In almost all languages, when the program finds an error, it raises so-called exceptions, but say, oh, I have this error, and you can quote this expression, this error at higher level of the call stack. So if you have a call A, if you have function A that call function B, that call function C, and you have an exception of function C, you can quote count this exception in a function. I forgot how I named them, but anyhow, in the higher level of the function calls. And then if these are not caught, they can terminate the script, and very rarely also sometimes also Julia, the whole Julia process can crash altogether. And the idea is that if we try some dangerous code where there could be some exceptions raised, we should put them in a try-catch block. So I try some potentially dangerous code, and then if some exceptions happen, I try to catch it and manage this exception. So here I have custom index where I have a vector, I have an index, and I can specify what to return. And I try to index in my vector with edx, with the index, and in case I have an exception, and in case this exception it is a bound error, I return instead this value to return. Otherwise I return I rethrow this exception, and hopefully this will be caught at a higher level somewhere in the code, or at least I don't know how to handle at this level. So I have 1, 2, 3, and if I get it normal way, I call the fourth one, I have a bound error, and if I use custom index, I will have my 0. Note, however, that exceptions are relatively expensive computationally, so don't use this in place of where you will use a normal if, normal conditional statement. Use it only really when you don't know exactly what could happen, but you want to have some guarantees to get to manage if a possible error, you have an idea of a possible error and you know how to manage it. And I'm showing you how to use exceptions, but exceptions are actually like everything in Julia objects, and they have a given type, and so you can look at the documentation of Julia if you want to create your own specific exception.